My work in this is really to support an understanding of decision makers' needs and to really work out where we can use forecasts to really inform decision making. We've had scientific developments and we've had new forecast products, forecasts particularly that come earlier in the season. So we have now forecasts that can come in May for the October, November, December season, which is one of the main growing seasons in Kitui. So very exciting. And we also have better forecasts for flood preparedness. So different kinds of forecasts, but then also for the decision makers, we've really been trying to help them understand what the forecasts say. What does the forecast skill mean? What does the probability mean? And how can they use that in their decision making? So we've been looking at specific decision making processes, early warning systems, and where we can bring in these forecasts.
Previously, the Kenya Meteorological Department has been issuing forecasts in form of rainfall tassels, which were not necessarily useful to their users because they could not be able to take action based on these rainfall tassels. So the forecast-based preparedness action has come up with a product where we can be able to improve our forecast by including probabilities and skill. Probability will be able to help a user define a threshold on on which one can be able to take action. When it comes to skills, the user is able to know from the skill of the forecast, a user is able to know how many times has a forecast been right or been wrong.
Currently, we are looking at the drought management plan and using indicators like the standardized precipitation index, which is part of what is used in the system, as well as vegetation condition index. And these are outputs that we've been able to produce over long leads, 6 months to the season, then 1 month to the season, and on a monthly scale for Kitui County. We've also been able to do a publication. This is based mostly for forecast producers. So we've been looking at what are the barriers for people not using forecast, especially in drought management. And one of the things that we found out is the technical capacity for people to understand the forecast and integrate it in decision making has been lacking. Secondly, is a lack of trust in forecast information. When one season goes wrong, then people lose trust. But when they are given skill information, which is one other thing that the project has been continually giving, skill information of how many times the forecast is right, has helped them build the capacity that yes, the forecast system is wrong in some instances, but you can find out of 20 times, 17 of those times it is correct. And this has helped build trust for these people. We've also been able to produce early action documents throughout the season, October, November, December 2019. We were interacting with the stakeholders in the county steering group that manages drought in Kitui County, to get them to narrate to us which actions would they take based on a forecast. So we'd present a forecast and ask them, what actions would you take? And recognizing the fact that the current system does not have financing for participatory action, so we asked the question in twofold. Considering the current system, what actions would you take with this forecast? And also, if we had an anticipatory fund, what exactly would you do? And we found that the bigger, most expensive actions are not able to be taken right now because we do not have a financing mechanism.
If we give information on climate information, especially to the stakeholders and the partners in Kitui County, they can make adequate decision in terms of preparedness so that they are able to manage the effects and the challenges of drought.
My name is Robert Matthews, and I'm going to talk about the CFLOOD project, which is a collaboration between researchers both in the UK and in Sri Lanka. So for CFLOOD, we're interested in tropical cyclones in Sri Lanka. So the right-hand panel here shows you various historical tracks of cyclones across the country, and typically they move from the east to the west. And we're interested specifically in compound flooding from these events. So this is where you get the combination of flooding from coastal flooding from storm surge coming inland and from river runoff coming down from the hills and mountains. So the specific region in which we're interested in is in the east of Sri Lanka, shown in the black rectangle in the left-hand panel here. And this is actually an elevation map of the country with areas that are below 10 meters above sea level, shown in red. And you can see that in our study area, there's a large area around the coastline that's quite vulnerable to storm surge that's colored in red. So for sea flood, we're developing and working with two different models. A hydrologic model, the input to this being rainfall, and then the hydrologic model gives us our river discharge and river flooding. And then we have a coastal hydrodynamic model, which uses the river discharge and simulates storm surge and waves, and then produces our compound flooding. But for the rest of this talk, I'm going to focus in on one of the inputs to the hydrologic model, and that's the DEM, or digital elevation model, used for the terrain. So as we were working on the project, we realized the importance of this digital elevation model for the study area. And you can see in this quote here, this has been recognized more widely too, that DEMs are critical for doing flood hazard mapping. So in Sri Lanka, as shown on this left-hand schematic here, there's actually no government flood hazard maps at the moment for the area in which we're working. There's only maps for the southwest of the country. There is, however, storm surge hazard maps for the area in which we're working, and you can see the colored in orange along the coastline, the area that was found to be vulnerable to storm surge. The other thing you can see from the storm surge hazard map is the complicated watersheds within the study area, and this is one of the reasons why the DEM is so critical for this region. So we've been putting a lot of attention into developing DEM for the region, which we will then make publicly available for other flood hazard studies to use. And to do this, we've been using OpenStreetMap and doing quality control of the stream networks from OpenStreetMap, and then using these stream networks to do stream burning of the NASA DEM, which is a brand new DEM from NASA for the globe.
Under the IPACE Malawi project, we've been developing and implementing an iterative participatory approach to identifying climate variables to incorporate in seasonal forecasts that can help to directly inform farmer decision making. We found that there's often a mismatch between the types of forecast information that could give farmers the necessary season-long foresight to inform decisions about crop and seed choice and land management practices, and the types of forecast information for which we have reliable model skill. Our approach has been to start with observation and mapping of farm level decision making processes and infer from these through focus groups some valuable agroclimatic indicators for our 3 districts in Malawi. These are indicators such as, for example, prolonged dry spell during maize flowering and grain filling stages, which are typically in February to April for our regions. We've worked with DCCMS, the Malawi Met Service, to test for historical correlations between these farmer-derived indicators and seasonal variables such as total rainfall, for which we've identified some skill in the seasonal forecast. But joining these dots has been difficult, and there are perhaps inevitably a lot of dead ends, i.e. potentially valuable indicators about which we just couldn't find any reliable associations. So we had to learn from that and in some cases make reasonable tweaks and adjustments to those indicators under circumstances in which we couldn't have quite as much participatory input as we probably would have liked. We're now working on using these correlations to make probabilistic statements within seasonal forecasts about the likelihood of those tweaked indicators, such as those relating to growing season dry spells, being realised. And we hope to revisit and potentially repeat the cycle of farmer engagement to evaluate the value of these probabilistic statements and to improve upon them.
Hello everyone, my name is Jivan Vincent Law from the School of the Built Environment at University of Reading. I'm very pleased to introduce our research work from the COSMA project looking at climate service for resilience to overheating risk in Colombo, Sri Lanka. So this is a collaborative project among the University of Reading and also Glasgow, Caledonian University in the UK and a number of the university and the partners in Sri Lanka. So we are interested to understand what's the heat exposure in Sri Lanka and what kind of mitigations we can provide to reduce that heat exposure. So this project involves a number of disciplines, including the meteorology, built environment engineering, architecture, and the planner. So this is a great opportunity that we can develop tools that be used by the end users and also have a looking at how the different disciplines could interpret the result from this tool in this project. We know that the heat exposure occurs outdoors and also varies across the city due to the urban heat island impact. The heat wave not only occurs outdoors but also occurs indoors because people spend a majority of time indoors. So how the building design have impact on the indoor exposure is very important. So from this project, we're interested to identify where is the hotspot in the city, and also what kind of buildings contribute to the indoor exposure most, and inside the buildings, what kind of human behavior could have impact on the indoor exposure. In terms of mitigation, we're quite interested in understand what's the role of urban design and building design have impact on the reduction of the heat exposure to the heat waves. So in order to address these questions, we need to develop a multi-scale modeling tools to identify and predict indoor exposure to the heat wave conditions and to identify what are the useful design strategies to mitigate such exposure. In COSMA, we are developing a multi-scale urban climate modeling framework consisting of 3 major components, from the regional weather forecast models using WRF to the urban climate modeling using SHEAR. SHEAR is a land surface model developed by Professor Sue Grimond in the Department of Meteorology at the University of Reading. And these SHEAR models consider the very typical urban features, including the urban density, urban morphology, building height, and also the anthropogenic heat to understand the urban climate and what's the urban design impact on the urban climate. And finally, the urban surface data, urban climate data will be used as the boundary conditions for the building climate models. So the building climate models can understand and predict indoor temperature and indoor thermal comfort and understand how the building materials and the building design, operation, building service, and also the people's behavior could have impact on the indoor temperature and indoor thermal comfort. And currently we have submitted one paper on the WRF-SHEAR coupling, and we are still working on the SHEAR and the building coupling. Basically, there are 2 ways of coupling between the urban scale and the building scale. One way is that the SHEAR as the urban climate modeling provide boundary conditions to drive the building climate models. Another way is the 2-way coupling. So the building climate models, the prediction data from the building climate models also have impacts on the urban climate models. So, but this is 2-way coupling is beyond the current COSMA project. So we are in the COSMA project, we will only looking at the 1-way coupling. We have applied this kind of a multi-scale urban climate modeling framework both in London and also Colombo, but we still refine the prediction in the Colombo. Apart from the modeling, we also conducted field monitoring observations in the cities and also inside buildings. One purpose of this field measurement is to validate our modeling results. So we are looking at different local climate zones in Colombo, working with the Glasgow Caledonian University to identify what are the different local climate zones in Colombo. And we have installed sensors in different local climate zones and are looking at different type of buildings in different local climate zones. For example, on the right-hand side is the local climate zone 3, looking at a compact low-rise neighborhood with single-family houses. So we install sensors outside buildings in this local climate zone 3 and also inside the buildings to record the temperature and the relative humidity and also humans' behavior. Unfortunately, because of the very difficult conditions in Sri Lanka last year due to the terrorist attack, and also this year due to the COVID-19 lockdown, and there's a very big disruptions to our field measurement campaign. So we haven't finished all the data collection. So we are looking forward some kind of extension of the project to have more time for us to collect more important data.